Hello everybody, welcome to week 6, Dynamical Systems 1. There is going to be 2 sessions on Dynamical Systems, week 6 and week 7. I will be your lecturer for the next 4 weeks, 5 weeks. This week we'll be talking about modeling systems not as agent-based models, but as sets of equations or maps. So, last week you worked in the behavioural space of NetLogo, where you learned about performing multiple runs in NetLogo, analysis in Excel, as well as learning some introductory work on Mathematica. Some work on the analysis of results, finding percolation and phase transitions for the forest fires model, some model fitting and determining the R0 for the epidemic model. He also did some visualizing of the results using Excel and Mathematica, as well as concepts of verifying, validating and replicating. So that was everything that you covered last week. This week we're going to be covering equation-based modeling. This is how we study dynamical systems if we aren't going to be doing agent-based modeling. This is where we have an equation and we want to understand how the equation describes a system. There are 2 distinct approaches to this. One is using discrete dynamical systems. These are called iterative maps. And so we'll work on some tutorial examples using exponential growth, the logistic map, and Lotka-Volterra equations. Then there are continuous dynamical systems. These are just differential equations that you would have come across at high school and probably in your first year of any technical degree you would have done. So we'll do some tutorial examples on that, on the simple harmonic motion, susceptible, infected, and recovered epidemiological models. And then ultimately we will do some analysis of dynamical systems, time series plots, phase plots, cobweb diagrams, and some other things. The work that we're going to be basing this week on is chapters 3 through 7 of Hiroki Sayama's Introduction to the Modeling and Analysis of Complex Systems. So if you want to see the text and follow along on that and see in more detail what we're going to be doing, then by all means have a read of those chapters. So, equation-based modeling. Here we're interested in the time evolution of a system expressed mathematically using equations. We want to distinguish between 2 particular types of dynamical systems: deterministic systems and stochastic systems. In deterministic systems, the systems are completely described by the initial conditions and the equations that then take the initial condition forward in time. That is different from stochastic systems, in which we have an equation which takes our initial conditions forward in time, but there is some randomness associated with that as well. So it's not completely deterministic. There's some statistical volatility in whether you go to state A or state B with some probability going forward. Deterministic systems are the ones that we're actually going to focus on in this course. There are 2 further distinctions in deterministic systems: continuous time, where we study those using ordinary and partial differential equations, and discrete time using difference equations, also called discrete maps. The stochastic systems will be the basis of CSYS5010, the complex dynamical systems time series analysis course that some of you will go on to study later on. So, dynamical systems. So a dynamical system is a system whose state is uniquely specified by a set of variables whose behavior is described by some predefined rules. These predefined rules are encompassed in something which we're going to call f. F is a function of the state of the system and either implicitly or explicitly the time variable. So in discrete dynamical systems we have the time evolution given by a map where the value of x at time t is given by some function of x at the previous time step at t minus 1 and t. This is called a difference equation, a recurrence relationship, or an iterative map. So this takes us from xt minus 1 forward to xt using f. In the continuous case, we have the time evolution given by a flow, which is just a differential equation where the rate of change of x as a function of time is given by this map, this function, this flow f, which is a function of x and t. Okay, so in dynamical systems, you've learned, the first question we want to ask ourselves is, have you learned of any models in the natural or social sciences that are formulated as either discrete time or continuous time dynamical systems? If so, what are they? What are the assumptions behind those models? Just want you to have a think about that. And then, what are some appropriate choices for state variables in the following systems? Population growth, a swinging pendulum, motion of celestial bodies. So by state variable here, we're talking about the x that we saw on the previous slide. So what is the x that we'd be interested in for population growth? What is it that's changing in time for population growth? And the swinging pendulum, what is the x which is changing in time for a swinging pendulum? And the motion of celestial bodies, planets, moons, and stars, is a function of time. Okay, so let's think about discrete time models. Our map is given as this function of x, our state variable at the previous time step, and t, and this function f allows us to calculate x at t. So what it produces is a series of values of a state variable x over time. So we have an initial condition, x0, and we plug x0 into f, and we use f at x0 and t, which here is going to be t equals 1, and f and x0 and t allows us to calculate x of t at the next time step. So if x0 is the input, then the output is going to be x1. If x1 is the input, then x2 is going to be the output. So this allows us to iteratively produce a time series x0, x1, x2, x3, etc. So this is the time series that we're interested in trying to understand. So as an exercise, I want you to think about a system that is made up of two interacting components. It's going to be A and B. Each component takes one of two possible states. It's going to be either blue or red. Their behaviours are determined by the following rules. A tries to say the same colour as B, and B tries to be the opposite colour of A. Now we can write down those two rules as functions, functions A and function B. These are our state transition functions. And so SA and SB are the states of A and B respectively. So we want to produce a time series SA-SB, starting with initial condition that both components are blue. So SA and SB at t equals 0 are going to be blue and blue. What would that look like? Well, here we have t at 1, is going to be B for SA, and B for SB. So at 2, we're going to have SA is going to try and be the same color as SB was in the previous time step. So SA at t equals 2 is going to be B, because that's what SB was at t minus 1. SB, on the other hand, is going to try and be the opposite color to what SA was at the previous time step. So at time step t equals 2, SB is going to be the opposite color of SA at time step t minus 1, which is t equals 1. So it's going to be red. And what happens at the next one? Well, SA wants to be the same color as SB, so it's red, and SB wants to be the opposite color of SA, so it's now red. Likewise, we repeat that. We find that for t equals 4, we find SA is red and SB is blue, and we can continue to fill out the table like this. And we end up with 2 time series. And each time point has 2 elements, a state for SA and a state for SB. So this is our time series. And we can see that there's a recurring pattern here. And so this is how, as we go forward in time, we have a function, or in this case functions, FA and FB, that map the previous 2 states at time t minus 1 to a new state at time t. And we can do that iteratively for as long as we like, and we can study the patterns that then emerge. So in linear systems, we have a dynamical equation whose rules involve just a linear combination of state variables. A constant times a variable, a constant, or their sum. Okay? In a nonlinear system, we have essentially anything else. So equation involving squares, cubes, radicals, trigonometric functions, etc. of the state variables. So linear systems are the simplest possible systems we come across, and in nonlinear systems, they're going to be everything else. We also have first order systems, and so a difference equation whose rule involves state variables of the immediate past at time t minus 1 only, whereas higher order systems are anything else. So for example, those systems that have a history to them, and so for example, the next state at time t isn't just dependent on t minus 1, it's also dependent on t minus 2, t minus 3. And you can see that there we now have, in some sense, a memory that is encoded in the history of the time series, which is then used to calculate the next time step. So that's what a higher order system means in this sense. We also have autonomous systems and non-autonomous systems. An autonomous system is a dynamical equation whose rules don't explicitly include time t or any other external variables. A non-autonomous system is a dynamical equation whose rules do include time t or other external variables explicitly. So those are the basic definitions of what we're going to be studying in terms of dynamical systems theory. In the next section, we're going to go over some examples for you to have a look at.